2005. In this section, we're going to talk about graphing exponential functions by hand. Okay, so trying to use those shifts and stretch and flips that we talked about way at the beginning of the year. We're going to apply those to these exponential functions. Okay, so in this first example, we're just going to consider a very basic exponential function, 2 to the x. We're going to fill out a table of values to figure out some ordered pairs, and then we'll go ahead and plot those ordered pairs to get a picture. Okay, so this is what we would refer to as the parent function, okay, the one that we're kind of starting with. We'll eventually start to shift and flip and stretch it to get different functions. All right, so let's go ahead and substitute in -2 for that x spot. Can we use an exponent property to rewrite that somehow? If you have a negative power, yeah. It would be in the bottom, right? So you can move the 2 to the bottom, and that would make the power positive. So we essentially have 1/4. So let's go ahead and plot that point. We plugged in -2, and we got out 1/4. Will be a little bit above the x-axis. All right, let's try the next one. Kind of going to work the same way. We have a negative power, so we can move it to the bottom. 2 to the first is just 2, though, so we're left with 1/2. So we'll go ahead and plot that ordered pair. What about 2 to the 0 power? Yeah? 1, good. And then the rest kind of get a little bit easier. 2 to the first is just 2, and then 2 squared, we have 4. Okay, so if we start to connect the dots, it looks like that exponential shape and we could probably throw in that horizontal asymptote at 0. All right, so based off this graph, they're going to ask us a few questions. I think we're going to be really good with these because we've done a few of them already. As the x value increases, what's happening to the y value? It's basically asking you about the right end behavior. So as the x's increase, what is the y value or the graph doing? Yeah. Approaching infinity. Good. What about the left end behavior? As the x's decrease, what happens to the y value or the graph? Yeah. Approaches 0. Good. And based off of the graph, do you think it's a growth function? Or why do you suppose it is a growth function? Yeah. There you go. Okay, so to the right, it moves away from the horizontal asymptote. Okay. None of that's new. We've done that in previous sections. Okay. This last part is actually not going to be too new for us either. It's just good practice. Bless you. Based on the 3 graphs at the bottom of some other exponential functions, which ones can we label as growth? Good, Rebecca? The second and third, right. As you go to the right, on both cases, you're moving away from the asymptote. So maybe we'll put G and G for those two for growth, which means we could probably label the first one as decay. All right. Let's go ahead and try another basic parent function. This time we have 1/2 to the x power. We're going to fill out a table, kind of work the same way as the last one we did. How can we make this power positive in this example? Yeah? Say it again, sorry. Flip it. Okay, so we can go ahead and flip the base. That would change to a 2. And since we flipped the base, the power would become positive. That's another way you can make a negative power positive, is by flipping the base. So 2 squared looks like we get 4. So we plugged in -2 and we got out 4. Let's go ahead and try the other ones. Alright, so connecting the dots, we have that exponential shape again. Looks like we have another asymptote, horizontal asymptote at 0. Let's go ahead and answer these questions based off the graph. Again, as the x's increase, what happens to the graph as you go to the right? Yeah. Approaches 0. Alright, what about the left end behavior? We thinking infinity? Okay. And why do you suppose this is an example of decay? Yeah. There we go. So to the right, it approaches the horizontal asymptote. Perfect. Okay. So this parent function was a decay example. Based off the 3 at the bottom, can we identify any other decay graphs? Yeah. The first and second, all right, which means the third one would be growth. We doing okay? So far so good? All right, so now let's go ahead. We're going to revisit these stretches and shrinks and shifting left and right and flips that we did at the beginning of the year, and then we're going to talk about how we can apply those to these exponential graphs. So from previous lessons, we've done different types of shifting and reflecting. We've had, I think, 5 different ways we can change a graph. All right, so maybe we'll first start off with, what if we have a negative on the outside of the function? What type of change does that do to a parent graph? Negative is a flip or a reflection, but you got to think about which one it is. Yeah, close. X. You had a 50-50 shot. Yep. Okay, so x-axis flip. Okay, now let's think about in terms of the ordered pairs. If you were to take a point above the x-axis and flip it below the x-axis, which variable is changing? Are you changing a y-coordinate or an x-coordinate? Yeah? A y-coordinate, because you're changing the height. You're going from above the x-axis to below. So we are saying that the y value changes sign. If you go from above the x-axis, which is positive, to below the x-axis, which is negative, a y value is changing a sign. Okay? What the other case is, what if we have a negative on the inside? What type of reflection is that? Yeah, the y-axis, good. And if you take a point on the right and flip it to the left, what variable is changing? Yeah, an x value, right? So the x value changes sign. Okay, let's see. What if we had either a plus or a minus on the outside of a function? How does that change your graph? Can we think back? These are the shifts. Or if we have a plus or minus on the outside, are we moving it left or right or up and down? All right. These are the up/down shifts. Depending if you're adding, you move up. If you subtract, you move down. If you're shifting a graph up and down, what variable is changing? Yeah, a y value. Okay. What if we have a plus or a minus on the inside, typically where the x variable is located in an equation? How does that move or change a graph? Yeah. Left or right, good. And if you're moving a graph left or right, you are changing x values. Okay. And the last one we had is if we multiply, I'll use a little dot to denote that, multiply on the outside. Do we kind of remember what that one does? That transformation? I know it's been a while. Hopefully these are coming back as we do them. Okay? This is the vertical stretch. Kind of like an accordion. You make it taller, stretch it out. All right, and if you're vertically stretching a graph, what variable are you changing, x or y? Yeah, the y value. Yep, so y value changes, we'll say y value multiplied by that a, that vertical stretch. Are those kind of coming back? I'm hoping. Okay. So we're going to take a parent graph. Notice how in this case we're going to use that 2 to the x like we did before. Do you see how in this transformed equation you have that 2 to the x, but there are other things listed in that equation? All those other things or numbers are some type of change. So what we're going to do is we're going to list those changes. We're going to describe how that changes the graph, and then we're going to try to actually graph the change, okay, based off those shifts and stretches and flips we can identify. So taking a look at this equation, can we identify any of these types of changes? This is the graph we're starting with, 2 to the x. What did this negative do? What did that plus 3 do? What did that plus 2 do? Yeah. Okay, so see how it's a plus 2 on the end. Normally, okay, we said for this parent graph, the horizontal asymptote was at 0, correct? But with this plus 2 at the end, now the horizontal asymptote is at a y value of 2. It's shifted up. Okay, so this plus 2, we'll say, is up 2 units. Notice how it's a plus 2 on the outside or the end of the function. All right. What about that negative out front, or that plus 3 kind of up in the power position next to the x? Yeah?
The negative out front is an x-axis flip.
X-axis flip, good. Okay. What about the plus 3 in the power spot? This is kind of considered the inside section. Wherever your x is, that's the inside of a function. If you add 3 on the inside, yeah?
It shifts the x values through.
Which direction? Left or right?
To the left.
To the left, yes. Okay, so way back at the beginning of the year, it was kind of hard for us to visually see this, and then we did some examples on the calculator. Anything listed on the inside of a function does the opposite of what you would think. That's the kind of tricky part with these transformations. So we see that plus 3 and we think, oh, it's probably going to move to the right, but it's actually moving to the left. Okay, and if you want to double check it on a calculator, you could. So we'll say another shift is left 3. Okay, do we remember a little, I forget if it's acronym or anagram, I'm not an English person whatsoever, but there was a certain process or method we had to use when we applied these transformations. Okay, order mattered. Do we remember which ones go first? Yeah?
Oh,
It's okay. Yeah?
I think the reflection.
Okay, reflection was first. So we identified one of those. We would have to do that first. Think about the alphabet. What comes after R? S. What do you think the S stands for? That's stretch. Yep. T. Okay, so that the T is a translation. That's the left or right and up and down motion. Okay, so we RST, just like the alphabet. We identified a reflection, so we have to do that first. We did not identify a stretch, so that's one less thing we have to worry about. But we did identify some translations, so we'll do those after we do the flip. Okay, so now that we know what these different changes are to the graph, how would they change the points on the parent function? Okay, we're going to use kind of these last examples we wrote up here at the top to help us with that. So normally an ordered pair starts off with x and y. But if we're doing some changes, we are going to be adding, subtracting, maybe multiplying some values to those variables. Okay, so let's think about this. The first thing we said we had to do is an x-axis flip. Which variable does that affect, and how does it affect it? Look at the top if you need to. Go ahead, Hannah.
Makes the y negative.
Makes the y negative. It changes the sign. Okay. Now let's go ahead to the translations. If we move it or shift it up to, which variable are you affecting and how are you affecting it? Yeah.
Adding 2 to the y.
Adding 2 to the y. Going up 2 units. What about the left 3? Go, Rebecca.
You subtract 3 from
You subtract 3 from
the
the x. Good. All right. So what we're going to do, we're going to recopy the table from the previous page we did. Okay, so this was the 2 to the x function. We had ordered pairs -2 and a fourth, -1 and a half, 0, 1, 1, 2, and 2, 4. Okay, those were on the parent function. But now we decided to change those. Okay, we're doing some shifting, some flipping. So let's see if we can figure out the new ordered pairs. We're going to use this ordered pair setup that we just wrote down and apply it to those points from the parent function. So let's see if we can figure out our first new ordered pair. This -2 is an x value, so if we plug it in for x, we'll have -2 minus 3, which would be -5. The 1/4 was a y value, so if we plug it in for y, we'll have -1/4 plus 2 would give us 1.75. Do you guys think you can plug in the other ordered pairs to get your new points? Let's see, can we get those ordered pairs? Do those check out? Okay, let's take a look at the next question. Where would the asymptote be on the g of x graph? So the g of x is right here. Okay, that's the new equation that we have after we have all these different changes to the parent. Where's the asymptote for that new function? Yeah.
2.
How'd you know?
Because instead of having nothing added on to the whole exponent group,
Right.
there's 2 added on.
There's 2. Okay, so y equals 2 because we'll say the parent graph was shifted up 2 units. Okay, that's what the plus 2 on the end is actually doing to the graph. So in previous sections, we've just been identifying the horizontal asymptote as what's being added or subtracted on the end. Okay, so I think we're good with that connection. But graphically, that adding or subtracting on the end is what's causing the asymptote to change. It's always starting at 0, but the moment you add or subtract something on the end, you're shifting it up and down. So that asymptote would be changing with those shifts. All right, so now let's go ahead and graph the function. We'll go ahead and plot these new ordered pairs that we identified. Bless you. All right, so we can plot the ordered pairs. We also said that the horizontal asymptote should be at 2. So let's go ahead and label that as well. And playing connect the dots, we'll go ahead and get our exponential graph. All right, so now that we have a picture, let's go ahead and kind of throw back here, we'll practice our domain and range analysis. So if you were to drag your pencil left to right, down to up, what could we identify as the domain or the range? Yeah. Perfect. And the range, low to high. There we go, negative infinity to 2. You can go all the way down, but you kind of stop at 2, but you can't touch it because it's that horizontal asymptote. How do we do with our first exponential shift graph? Okay, it's the transformations from the beginning of the year. We're just bringing them back and applying them to these exponential functions. Okay, let's go ahead and try another one. Can we identify the parent graph? Perhaps? Can you identify the base? Go ahead, Rebecca. 2 to the x, okay? It's just whatever base value you have and just a regular power of x. So anything else listed in that equation is some type of change that we have to identify. So can we start to list them perhaps? Yes, Tori? Sure. You said right 3? Okay. Down 2. All right. I like 2 of the 3. One of them is tricky. It is something we discussed at the beginning of the year that's always hard for us to kind of think back to. Will you see it? Yeah? It's left 3. Why? That's awesome. The negative on the inside is also affecting that plus or minus on the inside. Okay, so very good catch there. All right, so which one do we do first? Order matters. Yeah. The y-axis flip. Okay, did we identify any stretches or shrinks? No vertical stretch, right? Okay, so then the other 2 we listed must be those translations. All right, let's go ahead and write down what the new ordered pair would be. We normally start off with an x and a y, but if we're changing them, we're going to be adding and subtracting some things to these variables. So if we have a y-axis flip, yeah? Negative x. If we go left 3, which variable does it change? Yeah? Minus 3, okay, and then down 2. Yeah? Y minus 2, perfect. Okay, so what we got to do is take the original points from this parent function, plug them into this rule we have to get the new points, and once we have the new points, we can go ahead and sketch our graph. So let's go ahead and jot down the parent points. Okay, it's the same parent graph we had from before. We had -2 1/4, -1 1/2, 0 and 1, 1 and 2, 2 and 4. All right, so we're going to take those points, plug them into our rule, and we should get our new ordered pairs that we'll be able to plot. Since we identified that there was a down 2 shift, that means that horizontal asymptote is moving from 0 down to -2. Let's see, can we get that graph? Can we get those ordered pairs? Speak now, forever hold your peace. All right. How about we identify domain and range? Drag your pencil left, right, down to up. Good, Marie? Perfect. And range? Perfect. How are we doing? Okay. Do you guys think you can try the next one on your own? Do we need to identify the changes together, or do you think we're good with that? Should I take the silence as a we're good? Okay. All right, how do we do with the changes? Left 2, down 5? Can we identify those? All right, based off those changes, can we write the new rule we use for the ordered pairs? Okay, can we accurately use that rule to figure out where the new points are based off of where the parent points were located? Can we plot those new points? And how do we do with the domain and range? 2 thumbs way up? Perfect. Okay, we'll stop there for today. We'll take a look at 2 more of these graphing examples tomorrow, all right? And then we'll transition to the next section.